Hello friends, today we have retrosynthetic analysis, that is disconnection approach. This idea of disconnection was introduced by E.J. Corey, a great scientist in organic chemistry. A systematic framework was given by Stuart Warren, a well-known scientist. Chemistry of life is chemistry of organic compounds. And why this is to be done, that common needs of life, drugs, insecticides, pesticides, polymers, dyes, etc. all are organic compounds and improve the quality of life. Sources: natural or synthetic. Natural, very small amount obtained from large amount of natural material. The requirement is large, for example drugs. Thus synthesis in a laboratory is needed. Synthesis of organic compounds. Use of name reactions is very useful and very important, because there are many name reactions which can give the proper synthetic way, and the mechanism and stereochemistry must be understood for the particular retrosynthetic analysis. To devise a method for the synthesis, planning is required. Logical way is to go backward towards the starting materials by breaking the compounds to be synthesized. This is very important step. This is disconnection approach or retrosynthesis analysis. Retrosynthesis means what? Retro means reverse, go reverse. You will have a molecule to be synthesized, and you have to go backward, you have to go reverse to get the proper reagents. Art of planning synthesis or designing synthesis is retrosynthetic analysis. Disconnection, a reverse reaction, an imaginary process, a reverse of real reaction which break the bonds to give compounds from which the required compound can be prepared. Terms used in retrosynthetic analysis, that is target molecule, compounds to be synthesized. Retrosynthesis or retrosynthetic analysis, process of breaking down the molecule mentally or on a paper, or designing of molecule, commonly used arrows. That is, for example, if C has to be prepared, then we have to go for A and B react to give a delocalized structure. Retrosynthetic arrow, which is gives like that x plus y, and this is the retrosynthetic arrow. Disconnection is imaginary bond cleavage corresponding to reverse of the real reaction. Disconnection in such a way that it corresponds to a reliable reaction, or it may be a name reaction. For example, an insect repellent compound. This is a benzyl benzoate, which is the target molecule having an ester functionality, and this is the target molecule which can be synthesized from these two molecules. It means these are the two starting molecules, that is benzyl alcohol and benzoyl chloride. Another molecule, that is target molecule Tm, in which there is a amide functionality which can be getting from this particular benzoyl chloride, that is para-nitrobenzyl chloride, and the amine, that is the primary amine. What is the synthon now? Idealized, it is an idealized fragment resulting from disconnection. Fragment produced by disconnection, usually having the charge. Actually, the synthon is not a real species because it is having a charge, and we have to get the synthetic equivalent. Synthons are very important, because now in this particular step we can come to know that to break the amide we are getting two synthons, that is one has a positive charge, another has a negative charge. Carbonyl bond has positively charged carbon, whereas nitrogen of amine, which was actually the synthetic equivalent, has a negative charge. And now what exactly the synthetic equivalent or a real agent, that is the real chemical compound which can be we have in a laboratory, that it means that synthon is a synthetic equivalent is a particular compound or a real compound. For example, benzoyl, this is aryl chloride or benzoyl chloride, you can say. This is the anhydride, and can be synthetic equivalent or reagent equivalent for a particular synthon. This is the positively charged synthon. Now curved line to show that the bond has broken. What is by FGI? FGI is functional group interconversion, one functional group at the place of the other. This connection in such a way that it corresponds to a known reliable reaction. Now we know that this is the tertiary alcohol, that is tertiary butyl alcohol, and we have two different approaches to break this a particular molecule, a particular target molecule, and this is the first way by which we can have two synthons, that is positive and negatively charged species, unlike species, and not stabilized. Why they are not stabilized? Because CH3 plus means primary carbocation, and another synthon having negative charge which has an electronegative, more electronegative atom oxygen. And this is the another way to break, to go retro. That is the second way, in which carbocation is tertiary, which is more stable, and there is a hydroxyl anion more stabilized. This will be the more stabilized. We know that this is why this is stabilized, because this is a tertiary carbocation. So which is better? B is better than A, because synthons are stabilized and synthetic equivalent we have we have good synthetic equivalent, and which are present in the laboratory easily. One group disconnection. Look at the functional group. Let us take common functional group as OH. Again the example of tertiary alcohol, in which synthons A and B which are having positively charged species, and these are not real compounds. Now synthetic equivalent of A has this is the synthetic equivalent for synthon A, that is tertiary butyl bromide. Why Br is taken? It is a very simple technique that when the carbocation A, that is the synthon A, has a positive charge, so we have to take negatively charged species, that is Br minus is a negatively charged, and which is joined to the positively charged carbon, and another one is NaOH, because OH is minus, so Na plus would be there. So these are the synthetic equivalent for the preparation of tertiary alcohol, and this is what the exactly synthesis of tertiary alcohol from tertiary butyl bromide and sodium hydroxide. This is simple nucleophilic substitution, that is the SN1 reaction, because it is a tertiary butyl bromide.